one, this is a pipe made of glass. Then there are small crystals of red dye inside water. So the reason why we have the red dye is so that we can see movement of the water particles. Otherwise, you wouldn't be able to see it because it is colorless. So when we heat up this corner, can you tell me what is going to happen? Okay, there is going to be movement. What direction? You think it is clockwise? Okay, yes, you're right, but can we explain why? Huh? Heat? No. Okay, we know that definitely we must talk about density. But before that, why is there a difference in density? Okay, so let's see. Yesterday we said that when we heat up this portion, what happens to the spacing? Increase. When we heat up this portion, the spacing between the molecules, they increase. So because there's an increase in spacing, what happens to the volume that they occupy? It occupies more volume. What happens when more volume is occupied? Density decreases. How come? Because the mass doesn't change. We are not taking away particles. We are not adding particles. Mass doesn't change. Volume increase means density decrease. When density decrease, what happens? Yes, it rises. Okay, Harif can start answering my questions already. I need to see whether the rest actually know what's happening. So when density decreases, it will rise. Just like a hot air balloon, just like oil or water. So it rises. What happens as it rises? Are the particles up here just as hot as the particles at the bottom? Not yet, right? So as they move up, what happens? They encounter particles that are cooler. So what happens to the particles that are heated that goes up? They drop in their temperature. So they start to cool down and then they're being pushed to the right. And then after that, they cool further and they sink due to having a greater density. Then the cycle carries on, and you'll see a clockwise motion. Okay? Then over here we have an experiment that I explained to you yesterday. What direction do we see this moving? Also clockwise. Because the heated air is over here, this portion is less dense. This portion is denser because it is cooler. So there will be a convection current flowing this way. And the convection current draws the smoke particles inside. That is how we see air moving. So over here we have water moving, over here we have air moving. Both of them, different states, but collectively they are known as fluids. And convection is found in fluids. So there is a difference in density. That is why we have our convection current. When you talk about convection, I must see the keyword density. Finally, your geography. A sea breeze blows from the sea to the land. That is in the daytime. And they gave you a hint that the land heats up faster than the sea during the day. So during the day, the land heats up faster. Alright, then what happens to the air over land? If it heats up faster, what happens to the air over land? It rises. Why? So you see, you're still missing some key steps. No, not yet. Not about density yet. Okay, expansion. The spacing. We talk about the spacing first. More space between the molecules, more volume. More volume, less dense. Less dense, rise. Okay, so over the sea, it is denser, right? Why is it denser? Because it is cooler, so the spacing is smaller. Smaller spacing means smaller volume. Smaller volume means greater density. Greater density means it sinks. Don't drop, sink. Okay, rises here, sink here. So we will complete the cycle, and that is the explanation. In this explanation that's given, quite a number of keywords missing based on what we have just mentioned. So they did not talk about the spacing between the molecules. They did not talk about the volume. So I want you to include that in. based on what I've just said. If you understand, write it down in your own words. I will check. Don't just go straight from heat up faster, then become less dense. I want to know what's happening in between. Okay, done? We need small time. Okay, next. Did I still do AC? Oh, okay. So that's all for convection. Now, yesterday I said that I want to show you the simulation, right? Okay, so that's all we have for convection. So now, if you have noticed in our labs, right? Your library, some of the classroom, your AVA rooms, they have aircon. Where are the air conditioners placed? Top. Okay, generally, top, middle, or bottom? Top. Why? Okay, so make use of what we have just learned about convection currents. Think about it. Why are air conditions placed at the top? Okay, you have to say the whole. Tell me the whole sequence. Okay. Don't just start with cooler air is less dense. So what do you think? So in a room, we have an aircon here, AC. Okay, what happens when I turn on the aircon? So over here, first the inside will be cold, right? The inside of the aircon will be cold. The physics behind it, you can go and find out. Okay, it's very interesting also. So the particles that come into contact with in the region of the aircon, they are colder. Okay, particles over here, they are cold. What happens if they are cold? Why less dense? Why? Okay, particles are closer. What does that mean? What does that imply? Volume smaller. Of course, we are comparing with the other particles at the other corners of the room. Okay? So what if the volume is smaller for the particles near the aircon? Okay, density smaller. Okay, now what happens if the density is smaller, Kasha? Wait. Density? No. Density is greater. Smaller volume means the density is greater. So what happens if the density is greater? It starts with the letter S. Give me a letter. I. Okay, I. Huh? S? Size? No, not size. So you got one stroke already. What have sinks, yes, S-I-N-K. So they sink. Okay? All the cool air sinks. Why do we want the cool air to sink? Yeah, because the people are down here, right? You want to feel the cool air. So you want the aircon to be on top, then the particles will sink. Okay. Then we get this portion gets cooler. Then what happens on this side, this region over here? What can you tell me about the particles here? On other parts of the room? What can you tell me about spacing first? Okay, particles further apart. Okay, why are they further apart? Do you know? They have a higher temperature, so in other words, they have more kinetic energy. So the spacing between them is greater. Okay, so they are further apart. What does that imply? Okay, volume is greater, meaning density lower. Then what will happen? Rise, yes. So the particles over here, they rise. Then the particles over here, they sink. So as this happens, those that sink, they start to gain more energy, right? Because they are heated up. They come into contact with the warmer particles. They come into contact with your bodies, which has a higher temperature. So they will heat up. Then this portion, they flow towards the aircon and they get cool. So overall, I will have a net flow of particles this way. And this is my convection current. That's why we have the aircon at top. How many of you have been to cold, very cold countries? Okay. Do you have the opposite of an aircon? What is that thing called? It's a heater or radiator, right? So what does that do? It heats up the room, right? Where do we place that? Do we place it at the top? No, we place it at the bottom. So if I want to have a heater, I will place it at the top. H-E-A-T-E-R. Why do I want to place the heater on the bottom? Because I want the hot air to rise, and then the same process happens. So eventually the whole room will warm up. Whereas if I place it right at the top, then only the top will be heated up, right? Then the bottom is still going to be quite cold, which is not what you want. Yes, Moss? Oh, okay. So what if I have a heater over here and an aircon over here? Then I'm going to have a very good convection current that is being set up. Here, the heater will heat up the air, the aircon will cool the air. So you will have a very nice convection current happening. Then it depends on which one is stronger. Whether the aircon is more powerful or your heater is more powerful. If the power is equal, then we see which one is more efficient. But if they both work at the same rate, then you're gonna let it reach equilibrium earlier. That is possible also. Generally, this part will be warmer, this part will be cooler. Okay? Right, so that's an application for your convection. Okay, so the next part that I'm going to be talking about will be, what's the last one? Radiation. Now in radiation, what is the main difference between radiation and conduction and convection? Radiation. Okay, start with a C, it's not a physics answer. The radiation, the most important concept, does not require a medium. So what is this medium? When I was in secondary school, I didn't understand what this medium was. So right now, do you understand what medium is? Give me an example of a medium. What? Raise our hand. Yes. Okay, that is not in her physics sense. But what he said was quite interesting. Medium, in terms of religion, you know, medium, they use the same word, right? So it is. Okay, never mind. Let's not talk about that. But there are some concepts which we can try to draw that, make them quite similar. Okay, but let's just concentrate on physics. Give me an example of a medium. A pen. Okay, a pen contains particles. A pen is a solid, so there are particles. That is a medium. What kind of heat transfer can we see in a pen? Oh, okay. But right now I want to talk about this pen. What kind of heat transfer, what process will we see if I heat up one side? Conduction. So the medium will be the particles inside the pen, right? Okay, then he also mentioned a frying pan. So that is also another medium. What is the process of heat transfer in a frying pan? Also your conduction, because the particles are being heated up, they collide with each other and they pass on the thermal energy. Hey, the three of you can go and sit down already. Give me another form of medium. So far we have talked about solids. Other forms, other types of mediums? Liquid can be a water. So water, what kind of process takes place for heat transfer? Convection, right? So again, we have particles inside water. They transfer the heat. They are the medium. We also have a little bit of conduction in water. Okay? And what about gases? There are gas particles also. So we can feel the wind. This is actually the air particles hitting our skin. These particles, they are also our medium. So we consider air as a medium also. So far, conduction, convection, they require medium. So this thing called radiation does not require a medium. When is it that we don't see a medium present? Gail said air. Do you agree that air is not a medium? Air has particles, right? So air is a medium. Can you give me an example when medium is absent? In space, okay, in space where there is vacuum. So for example, between the sun and the earth, is there air? I mean, besides our atmosphere, if we don't consider our atmosphere, there is no air in space. So we know that since there is no air, you cannot have conduction, you cannot have particles bringing the heat energy, the heat from the sun, collide, and it reaches the earth. Cannot be, no conduction. There cannot be convection also, because convection requires difference in density. And to have a difference in density, you need mass. In other words, you need particles. If there are no particles, there is no mass, then there's no difference in density to talk about. There cannot be convection in space. That leaves us the last form of heat transfer, which is by radiation. This is the one that allows heat to be transferred from the sun through the space, through a vacuum, meaning no medium, and it reaches the earth. That's how we feel. That's why we feel hotter in the afternoon as compared to the night. Okay? So what other things do you remember about radiation? Any keywords that comes to mind? Sorry? Infrared, is it? Infrared radiation. Okay, what else do you remember? Okay, EM waves. Any more? Sorry? UV rays. Okay. UV rays. Any more? Y'all are just. Y'all are. Okay, this part. These are different types of waves. Okay, your UV rays, your infrared rays, they are different types of waves. They are all a subset of this. Okay, then your nuclear, because you think about the accident that happened in Japan, there was a nuclear accident, so there was radiation leakage. Okay, different types of radiation. In this sense, in terms of heat. Okay, so not too concerned about these things at the moment for our topic. What else can you remember about radiation? Something about color. Remember anything about color? Or be more confident, I need to hear. Absorber, okay? So should we say absorb? Okay, then I have black. What else? Shiny. Silver. Matte. Any more? Rough, okay. Smooth. These are keywords that are associated with radiation. And let's see how we use them. Okay? Turn with me to your textbook. Page. Yes, 138. Textbook, page 138. Under radiation. So they say this is the transfer of thermal blah 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 medium. So highlight the whole thing. You need to memorize. Then it can take place in a vacuum. Oh, but does that mean that it can only take place in a vacuum? Okay, so I want you to include this point. It can also take place when there isn't a vacuum. Meaning, in our classroom, there is also radiation. And our classroom is not a vacuum, right? We can still have radiation here. When we step out into the sun, into the field right now, we're going to feel the heat. There is air around us. Radiation can take place in the presence of air also. It doesn't take place only in a vacuum. But its characteristic is that it is the only type of heat transfer that can take place in a vacuum. You know the difference, huh? Okay, so let's talk about the emission of infrared radiation first. At the bottom of page 138, you see the blue words, emission of infrared radiation. All objects and surfaces that emit, that means they give out infrared radiation. That includes you. You are giving out infrared radiation. And because you give out, because a body, for example this calculator, it gives out infrared radiation. So its temperature will drop after it gives out enough radiation, because it is giving away heat. Okay? Then we will see how the surface of the calculator, the surface of anything affects the radiation, the process, the rate of radiation. So in your next page, investigation 8.5. This is what I want you to write. Okay, you have this word. Write down at the top, emission of infrared radiation. Spell it out. So you know that this experiment is specifically used to investigate the rate of emission. Okay? Earlier on we heard another word, right? Absorption. Absorption and emission are opposite. Emission, you give out. Absorption, you take in. So this experiment is only for emission. So what do we have? We have two tins. Okay, one black tin. And they said that, yeah, it's just black. Then another one, we have a shiny one. I am just going to use yellow color to represent the shiny tin. And inside, we have boiling water. Let's use red color. Boiling water. Now, we know that after some time, it is going to, the containers, they're going to cool down. When you give it enough time, temperature will drop. But which one will drop first? Why? Okay, now we are talking about heat being released. So I'm just going to use this red color to illustrate that, oh, your heat is being released out in the form of radiation. So we are talking about emission. Emission of radiation. Which one emits heat at a higher rate? Yes? Which one will emit heat at a higher rate? So based on the experiment, they take the temperature every few seconds and they realize that, hey, the black color tin, temperature drops faster. So that is shown in our graph. You have a blue graph and a red graph. The blue graph is for the black tin, showing that as time passes, temperature drops faster. It has a steeper gradient. Okay? So the graph over here, this is what you have in your textbook. Shiny and black. So at any given time, for example, time equals to 10 seconds. That is your temperature. Time. At time equals to 10 seconds, the temperature for the black tin is lower compared to the temperature of the shiny tin. So then we can conclude that the black tin is emitting heat at a higher rate. Let us try for maybe time equals to 30. At time equals to 30 seconds, the temperature for the black tin is still lower than the temperature for the shiny tin. So based on the graph, we conclude that the black tin emits heat at a higher rate compared to a shiny tin. Understand what this experiment shows? Then at the end, they all reach the same temperature. What do you think this temperature is? Yes, what do you think this temperature is? Finally, when they all reach the same temperature. Huh? Room temperature? Is that what you said? Yes, you're right lah. Room temperature. Because a cup of boiling water, you place it in a room long enough, it will reach your room temperature. Okay? Then the conclusion at the bottom of the page, please go and highlight it. Dull and black surfaces are better emitters of infrared radiation than shiny and silver surfaces. So we have covered these keywords: shiny, silver, black, and you missed out dull. But dull is kind of like matte. Okay, so yep. That is the conclusion you must know. Then next page, page 140. What do we have at the top? Absorption of infrared radiation. Earlier on, it was our emission. Now we consider absorption. Just like the example earlier on, my calculator. Although it is emitting heat, it is emitting radiation. At the same time, it is also absorbing radiation. So we see how the surface of different objects affects the rate of infrared absorption. So now we have two temperature loggers, two sensors. Okay, they are, and I'll use black for this. You can just treat it as a thermometer inside. And another thermometer over here. And we place a heat source. In this case, they use a light bulb. Or I can choose to set up a fire over here. Okay, then this side is black color aluminum foil. On the left side, I have the shiny one, represented by blue color. As you heat up both of them, their temperatures will increase. But one of them will have temperature increasing at a higher rate. Which one is it? According to the experiment, according to the graph that they plot, they realize that the temperature will look like this. So the lower one is shiny, and the one on top is black. This is your temperature, and this is the time again. So at any one point in time, for example, 10 seconds, the temperature for the shiny one is lower than the temperature for the dark one, meaning our black surface is absorbing heat at a higher rate than the shiny surface. That's why its temperature is higher at the same time. We can draw more lines to see the relationship. So maybe at time equals to 20 seconds. We see that the time for the shiny surface, the temperature for shiny surface is still lower than the temperature for the dark surface. So interpretation of the graph, the conclusion will tell us that a dull surface, meaning the black one, dull and black surfaces absorb infrared radiation faster as compared to blah 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 blah. Highlight this part at the bottom of your page. The full one will be infrared radiation. You can leave it as radiation also. Okay? Then there are some other factors that affect the rate of emission and absorption of infrared. But before we get there, when you make, for example, your CCA t-shirt, your class t-shirts, especially for those who are in CCAs that require you to be outdoors, what colors will you all choose? Or what colors do you all tend to avoid? Okay, black. Why? Because it's hotter, but why? So now we learn that black color is a good absorber of heat. Should we talk about emitter? Is it necessary to talk about emitters of heat when you are considering the color for your CCA t-shirt? No, right? Because we are concerned only about absorption of heat. Although black color is also a good emitter of heat, but it depends on the context of the question. What are we interested in? We are interested in only the absorption So we talk about absorption only. Don't go and confuse yourself and think, hey, if I wear a black colored t-shirt, although I am absorbing heat faster, I'm also emitting heat faster. So doesn't that mean that the net transfer of heat is zero? So it shouldn't make a difference. So don't think that way because it is dangerous, it is wrong. Although black color is also a good emitter of heat, the rate of emission, in this case, is likely to be slower than the rate of absorption. So, all in all, you will still feel the effects of the sun, the heat from the sun, on you when you wear your black colored t-shirt. Okay? So context is very important. We only talk about absorption only. Or we talk about emission only. Okay? For example, if I talk about having a drink, I have a mug of hot Milo over here, and then I have another mug of hot Milo. Then this is shiny, and this is black. Okay? I want my Milo to stay hot. So which cup should I put my Milo in? I put it in a shiny one, right? If I want it to stay hot. So what should I be talking about if I want to explain? Should I be talking about absorption or emission? I should be talking about emission of infrared radiation only. I don't need to talk about the absorption. Understand? Yeah? So other things that will affect will be your surface temperature. Highlight it. On page 141. Affects radiation. The higher the temperature relative to the surroundings, the higher the rate of emission of infrared radiation. Alright, so the room temperature in our classroom is probably about 32 degrees. What is your body temperature? About 36, right? Is that higher than the room temperature? Yes. So if I were to take a infrared sensor, those kind of camera, right, that can detect infrared radiation, then I take a video of this room, I will see you guys being orange, yellow, as compared to the surroundings, which is, probably will be red also if you're having a fever. As compared to the surroundings, which probably will be blue to represent that it is colder. Then what happens when I take the video of a fire over there? It is going to tell me that, hey, that fire over there is hotter than your temperatures. So in other words, the higher the temperature, the higher the rate of emission of infrared radiation. Okay? So sometimes at night, if you want to see whether there are people moving around, but it is pitch black, maybe you're in the forest, okay? Then you do not know whether there's somebody in the vicinity. You have an infrared camera. You can use that to just scan around because it picks up infrared radiation. As long as there's something that is of a higher temperature, it will show you. Maybe it will show you as red, yellow, orange, those kind of colors. Okay? Maybe you've seen that in the movies or on TV before also. Sorry? The goggle one, the green color vision, that one is different. It's not infrared. Yeah, it's night vision goggles. It works on another principle. Okay? Then next one is on your applications of thermal energy transfer. We have finished on radiation already. We move on to applications. Actually, as we were progressing, we have already learned the different types of application. This is on page 142, 143. We talked about the frying pan. We talked about the handles. We talked about aircon, water being cooled. These are the different applications of the processes, and there are three types. So you need to identify which process is more dominant, because more often than not, it is not just one type of process. Usually it is a combination. Okay? So cooking utensils on page 142, usually we use metals because they are good conductors of heat. We want the food to heat up quickly. Soldering iron. Gaius, have you used soldering iron before? When? DNT. What is it made of? The tip, just the tip. Yeah, for the soldering iron. What color is it? Huh? Silverish? Probably you will see it as copper color. Yeah. Or maybe it's a different model. But basically, the tip of the soldering iron must be a very good conductor of heat so that it can melt your soldering iron. When the what? Heater? Which material are you talking about? So copper, you must choose a material that can conduct heat very well, yet it has a high melting point. So that's where you apply your physics in choosing what materials to use for different items. Okay? Then I'm just going to skip the heat exchanger. Then we have poor conductors of heat on page 143. Your cooking utensils, we have rubber or plastic handles. Those are poor conductors of heat so that you don't hurt your hand when you pick them up. We also have this kind of windows, double glazed windows. It is not just one panel of glass. You actually have a layer of air in between them that reduces heat loss through conduction. Because the particles inside are spaced very far apart, conduction does not take place easily. Okay, so we see this type of windows in colder countries where they want to keep the heat in. Then we talked about the air conditioner already. Your electric kettles, why the heating element is at the bottom? Because we want convection currents. Radiation, okay. Turn with me to page 146. Your design of the vacuum flask. The vacuum flask involves many different components that try to reduce heat loss to the surroundings. You have conduction, convection, and radiation. So take some time to read through the different parts. 1, 2, 3, 4, 5. 5 of them. Five components on how we reduce heat loss to the surroundings. We keep your liquid inside hot or keep your liquid inside cool.